Welcome back to the video course on fluid mechanics. The last lecture we were discussing about the dimensional analysis, and we have seen the various laws like Reynolds number law, Froude number, then various other dimensional numbers, and then we were also discussing about the various similarity or similitude theories. So, we have seen basically there are three fundamental similitudes or similarities which we have to say observe or we have to deal while modeling. So, these are first one is geometric similarity, and the second one is kinematic similarity, and third one is dynamic similarity. So, in the geometric similarity we will be looking for the similarity or similitude of the length, breadth and height, or the area or the volume which with respect to the modeling which we do. And in the second similarity, like kinematic similarity, the similarity of the prototype and the model will be dealing with, and the correspondingly the velocity, acceleration type parameters will be, its similarity will be considered. And the third similarity is the dynamic similarity. In the dynamic similarity, the forces acting on the model or the prototype is considered, and its ratio is considered. So, the forces like viscous force, shear stress or shear forces, then the pressure, all these aspects are considered in the dynamic similarity. So, this while doing the physical modeling in the laboratory with respect to the real field case or the prototype, we have to see that this geometric or kinematic or dynamic similitude or similarity are kept. So, now say when we discuss about the similitude or similarity in the modeling. So, we will say that a complete similitude between the model and prototype are met whenever we consider geometric similarity, kinematic similarity and dynamic similarity. So, we say that in the case of a model, whenever the system is geometrically, kinematically and dynamically similar, we say that there is complete similitude is achieved with respect to the prototype and the model. Or generally, as we have seen earlier, say when dynamic similarity is met, actually the kinematic as well as geometric similarity also considered. So, even if we say that the model which we do in the laboratory with respect to the real case or with respect to the prototype, then we can say that the complete similitude is achieved. So, here in this slide you can see say the prototype and the model. Here you can see this is the prototype and this is the model. So, when the dimensions are considered and then its similarity is met, then we say geometric similarity, and then here the velocity or acceleration other parameters are considered, then we say kinematic similarity, and then the forces are say considered and then similarity is met, then we say dynamic similarity is met. So, in the complete similitude or complete similarity, the geometric, kinematic and dynamic similarity are met with respect to the physical modeling and the prototype. So, now with respect to this, say here we can see say a flow over an airfoil. So, here the flow is coming and then you can see that airfoil is considered, this is the prototype and then here this is the model. So, corresponding to the prototype you can see that the geometric similarity is met by considering the shape, size with respect to length, width and other parameters. So, geometric similitude is scale, model is scaled according to the geometric similarity or geometric similitude. And then second one is the kinematic similitude, the fluid streamlines are scaled. You can see here with respect to this figure and this figure with respect to prototype and the model. So, here you can see the streamlines are also scaled. So, accordingly we can say that kinematic similarity is met. And the third one is say here you can see the various forces acting like drag force, lift force. So, with respect to that also considered, then we say that the dynamic similarity is met. So, here the lift of the prototype divided by lift of the model, that is equal to drag divided by drag of the model. So, like this, then we say that dynamic similarity or dynamic similitude is met with respect to the modeling. So now say say while doing all this similitude are considered depending upon the problem. So we have seen earlier a number of dimensionless numbers like Reynolds number, Fruit number, then Weber number, Euler number, etc. So we consider these dimensionless numbers, and then we can derive similarity with respect to these dimensionless numbers depending upon the type of problem. So if we consider, say for example, say if we consider the closed conduit flow like pipe flow, there actually we have to see that the governing parameter, governing dimensionless number is Reynolds number. So we will be choosing the Reynolds number similarity between the prototype and the model. So for closed conduit analysis, we use Reynolds number similarity. So similarly, depending upon, say for example, open channel flow, flow through weir or flow through say flow over a dam or a spillway. So then we consider the major force is here is the gravitational force. So with respect to this, we can see that there will be free surface also. So in these kinds of problems, we model using the fruit number similarity. So similarly, we can see that wherever the pressure difference are considered, the pressure difference between the various sections are important. So we consider the dimensionless number corresponding to the pressure. So we can consider the Euler number similarity. So in situation where pressure difference are important, we consider Euler number similarity. And say for example, compressible flow like flow over an airfoil, the compressibility like gas flow compressibility is considered. In that case, we will be using Cauchy number similarity. And then say wherever like the compressibility effects predominate like motion of rockets, then there we consider the Mach number similarity. So Mach number is related to the compressibility effect. So we use the Mach number similarity. So similarly, wherever the surface tension effects are important, so like analysis of thin film flows and formation of droplets, in that case we can use the Weber number similarity. And then say like in unsteady oscillating flow problems, there the vortices observed behind a stone like in stone in a river. So there we can consider the Stauhal number similarity. So like this, we have seen various dimensionless numbers. So Reynolds number, Fruit number, Cauchy number, then Mach number, Weber number, Stauhal number. So between the prototype and the model which we can consider with the similarity of this model and the prototype with respect to these dimensionless numbers, and then we can derive various laws based upon these dimensionless numbers to get meaningful results in with respect to the physical modeling. So now with this similarity with the dimensionless numbers we consider, generally most of the fluid mechanics problem, the most important dimensionless numbers which will be commonly used are the Reynolds number and the Fruit number. So here in this lecture we will be considering only Reynolds number similarity law and the Fruit number similarity law. Similar way we can consider other laws also. So here the similarity laws or model laws. So as we have seen, first we will be here we are considering the Reynolds model law. So as I mentioned, say the Reynolds number similarity between the model and the prototype are considered. So we can write the Reynolds number of model is equal to Reynolds number of the prototype. So correspondingly, so if we consider the Reynolds number is generally represented as rho VL by mu, where rho is the density, V is the velocity, L is the characteristic length, and mu is the coefficient of dynamic viscosity. So with respect to the model, we can write rho m Vm Lm by mu m, that is equal to, with respect to prototype, rho p Vp Lp by mu p. So, now if you consider the ratio between the model parameters and the prototype parameters, so we can write rho m by rho p as rho r, and V m by V p as V r, and L m by L p as L r, and mu m by mu p as mu r. So, we can write this correspondingly rho r V r L r by mu r. So, this should be equal to 1. So, now, if you instead of coefficient dynamic viscosity, if you consider kinematic viscosity, this we can write as V r L r by nu r, that is equal to 1. So, here r corresponds to the scale ratio. So, as we have seen, we will be using a particular scale ratio. So, with respect to the geometry or with respect to other parameters. So, this r represents the corresponding scale ratio. So, now if we use this Reynolds model law, so correspondingly we can, for various parameters like velocity, acceleration, discharge, pressure, energy, power, etc., we can use this Reynolds model law to derive various scale ratio. We can derive the scale ratio using the Reynolds model law. So, this here very similar way here this slide, as I mentioned, using the Reynolds similarity, we can derive the various scale ratio. So, if we consider the velocity, so this velocity ratio with respect to the Reynolds similarity, we can write V r is equal to mu r by L r rho r. So, here you can see V r is equal to corresponding to mu r by L r rho r, where mu is the corresponding coefficient of dynamic viscosity, L is the length, and rho is the density. So, similarly, if you consider the time ratio with respect to the Reynolds similarity, we can write rho r L r square by mu r, and the acceleration ratio we can write mu r square by rho r square L r cube. So, all these parameters we are deriving with respect to this Reynolds model law, and r corresponding to the scale ratio. So, similar way, if you consider the discharge with respect to the model and the prototype, we can derive the scale ratio as mu r L r by rho r, since discharge is equal to V r into L r square. So, this gives Q r discharge ratio as mu r L r by rho r. Similarly, pressure ratio P r we can write as rho r into V r square. So, that we can write as mu r square by rho r L r square. So, similarly, energy ratio we can write so mu r square L r by mu r, or rho r nu r square L r. So, this gives the energy ratio. So, these different say parameters which we consider while doing the physical modeling with respect to the prototype. So, the various scale ratio we can, for various parameters like velocity, discharge, or pressure, we can derive using this equation, and then correspondingly we can do the experiment in the model, or we can develop the model and then run the experiments. So, correspondingly the Reynolds similarity will be met. So, this is with respect to the Reynolds similarity. So, here only few parameters are listed, but in a very similar way other parameters also can be derived and can be expressed as ratios with respect to the Reynolds similarity. So, the second one, the other important similarity law or model law is the fruit model law. So, here as I mentioned, the fruit number is say with respect to the effect of it indicates the effect of gravitational force. So, the cases like say open channel flow, various hydraulic structures, we can use the fruit model law. So, as per this fruit model law, we can write the fruit model is equal to fruit prototype. So, with respect to the fruit number, so we can write this fruit number is generally expressed as V by root g y. V is the velocity, g is the acceleration due to gravity, L is the characteristic length. So, we can write corresponding to this model, we can write V m by square root of g m L m. So, that is equal to corresponding to prototype V p by square root of g p L p. So, in a very similar way as we have seen the Reynolds model law. So, here also if we consider the ratio between the velocity, length and acceleration. So, we can write here V r by root g r L r. So, that will be equal to 1. So, this we can write as now the velocity can be written as square root of LR. So, where R stands for the corresponding scale ratio. So, now most of the cases, so corresponding to the prototype as well as the model, generally we do in the laboratory with the gravitational scale will be always 1, since if we are not going for centrifuge modeling like with high gravity 10 g or 50 g, then the case is different. But here most of the laboratory models which we develop will be with the prototype as well as the laboratory model will be with respect to same gravity, acceleration due to gravity will be same. So, we can write this Gr is equal to 1. So, we can write now Vr is equal to square root of Lr with respect to the fruit model law. So, this gives the fruit model law. So, now using this we can derive various the scale ratios for various parameters, as we have seen in the case of Reynolds model law. So, now the same the fruit model law is we can use with respect to various parameters. So, the next slide shows how we can utilize it here. So, using the fruit model similarity, force ratio we can write as Fr is corresponding to Lr cube rho r, and where L is the characteristic length, rho is the density, and r is the scale ratio. So, time with respect to fruit similarity law we can write Tr is corresponding to Lr to the power 1 by 2 or square root of Lr, and then acceleration ratio you can see that here fruit law is considered, the acceleration ratio here is Gr is corresponding to 1, since as I mentioned we are doing experiment the same acceleration due to gravity with corresponding to prototype. So, acceleration ratio Gr is equal to 1, and then the velocity ratio, as we have already seen, Vr is corresponding to square root of Lr or Lr to the power 1 by 2, and a discharge ratio is correspond Qr is Vr into Lr square or Lr to the power 5 by 2. So, that gives discharge ratio with respect to the fruit number similarity, and then work is we can write work ratio is considered, we can write Er is corresponding to rho r Lr to the power 4, and power ratio we can write rho r Lr to the power 7 by 2. So, like this here only few of the important parameters are listed. So, very similar way we can derive the scale ratio with respect to the fruit number similarity, we can derive the scale ratio, and then we can correspondingly model in the laboratory with respect to the prototype. So, now say as I mentioned, Reynolds number and fruit number are the two most commonly used dimensionless numbers or similarity principle, similarity laws. So, let us see some of the important applications for if we consider the Reynolds model law. So, like Reynolds model law, you can see that say cases like completely submerged flow. So, if you consider if you are modeling say the aeroplane or say airplane with respect to the laboratory. So, we generally will be considering the Reynolds model law, and then say it is completely submerged airplane or torpedo, all these kinds of modeling we will be using the Reynolds model law. And then second one is completely enclosed flow. So, Reynolds for enclosed flow like pipe flow, Reynolds number is more important. So, we will be using the Reynolds model law. And then as a third case is viscous flow like settling of particle like reservoir sedimentation or the dust settling, all these cases the Reynolds model law will be important, and we can utilize the Reynolds model law for these cases. So, similarly as I mentioned, fruit law is concerned or fruit number is considered, you can see that wherever the say gravitational effect is more important, fruit law is considered. So, say cases like wave action, so like say actuary models or like say Portland Harbor models, these models we can use the fruit law. And then problems with free surface like is a flow over a spillway, we can use for fruit model law. And also hydraulic structures like dams and then weir, all these kinds of problems we can in modeling of these problems we can use the fruit model law. So, As I mentioned, since Reynolds model law and Fruit model are two most important model laws in physical modeling, we generally use the physical modeling. So, here we have described only Reynolds model law and the Fruit model law. So, very similar way we can derive the other model laws and corresponding scale ratios, and depending upon the problem we can utilize the other model law. So, now before proceeding to further aspects of physical modeling, let us consider two examples with respect to Reynolds model law and the Fruit model law. So, first case is example on Reynolds number similarity. So, here we consider a problem, a model of airplane of scale 1:20 is tested in variable density wind tunnel. The prototype plane is to fly at 500 km/h in atmospheric pressure. The pressure used in wind tunnel is 25 times the atmospheric pressure. We have to find the velocity of the model, and if the velocity to be used in the model, and if the measured drag in the model is 1000 Newton, what will be the corresponding drag in the prototype. So, this is the problem. So, here we consider an aeroplane. So, with respect to the aeroplane, so you can see that we are considering a wind tunnel. So, for the wind tunnel we are developing a model with respect to this is wind tunnel and aeroplane model. So, here the details of this, if you consider the prototype, and this is the wind tunnel model. So, with respect to this, so here we have to say we are modeling the aeroplane which is flying at the rate of 500 km/h. So, with respect to this we have to consider the modeling here. So, now for this problem, so as I mentioned, the Reynolds model law is important. So, if we consider the Reynolds model law, rho m Vm Lm by mu m is equal to corresponding to the prototype rho p Vp Lp by mu p. So, here the scale ratio for with respect to length is considered. Lm it is given as 1:20. So, Lm by Lp is Lr is equal to 1/20, and viscosity. So, here we consider air both cases. So, is remaining constant. So, if you assume the viscosity remain constant, mu m is equal to mu p, and if you assume constant temperature also, we can write P by rho is constant. So, the pressure by density is constant. So, on that assumption we can write the pressure ratio Pm by say Pp, that is here it is given that the pressure used in the wind tunnel is 25 times the atmospheric pressure. So, that means Pm by Pp, the model and the prototype, that is equal to 25. So, we can write that is equal to rho m by rho p. So, now from the Reynolds number similarity, we have already seen that this the Vm can be represented as Vm is equal to Vp into mu r by rho r L r. So, this gives the velocity of air in the model. So, Vp is the velocity of the prototype. So, mu r is the viscosity scale ratio, rho r is the density scale ratio, L r is the length scale ratio. So, now Vp, the prototype velocity is given as 500 km/h, and then mu r is already constant, and then rho r, here you can see it is say here 25, and L r is 1/20. So, we can write 500 into 20/25. So, that gives 400 km/h. So, now say here the ratio of the model velocity to the prototype velocity is Vr is equal to Vm by Vp. So, that we can get as 20/25, and the force ratio, as we have seen, force ratio we have to consider drag force here. So, force ratio is equal to Lr square rho r Vr square. So, the length ratio is considered as 1/20. So, 1/20 square, rho r is 25. So, Vr is 20/25. So, 20/25 square. So, this we can get as 1/25. So, force ratio with respect to the model and prototype comes 1/25. So, hence the drag at prototype, so it is given as the model, the drag is given as 1000 Newton. So, Fp is equal to m by Fr. So, that will give 1000 into 25. So, we get the drag as 25,000 Newton. So, this is a simple problem where the Reynolds model law is applied. So, very similar way different kinds of problems wherever Reynolds number is predominant or is important, we can use the Reynolds model similarity to solve these kinds of problem. Second one is we consider an example is here fruit number similarity. So, here the problem is for a spillway model of 1:10, estimate the velocity of prototype corresponding to a model velocity of 2 meter per second, discharge of prototype per unit width for model value is 0.5 cubic meter per second per meter, pressure head in the prototype for the model head of 10 centimeter of mercury at a point, and then energy dissipated per second in the model for a prototype value of 5 kilowatt. So, here what we consider is a spillway. So, here if we consider a spillway like this, so this is the prototype, the flow is taking place like this. So, if you consider a small model of scale 1:10 corresponding to this is prototype. So, here we have the model. So, we have to consider the problem like this. So, the scale is given say 1:10. So, for this problem we have to consider, we have to determine the velocity of prototype, then discharge of prototype, and then pressure head in the prototype and energy dissipated per second. So, here now so as I mentioned, this particular problem is considered, say this gravitational effect is more important. So, fruit number similarity we can directly use. So, if we use here the fruit number similarity, so we have already seen the velocity ratio is length scale ratio to the power 1/2 or square root of LR. So, length ratio is given as LR is equal to 1/10. So, velocity of prototype, and we can write Vp is equal to Vm by LR to the power 1/2. So, Vp is equal to Vm is 2 meter per second. So, LR is 1/10. So, 10 to the power 1/2. So, this gives 6.32 meter per second. So, this is the first part of the question. Second part of the question is ratio of discharge per unit width. So, that is QR is equal to VR LR. So, now QR is equal to QM, this M and P, M is corresponding to model, P corresponds to prototype, R corresponding to the scale ratio. So, QR is equal to QM by QP. So, that is equal to VR LR. So, that is equal to LR to the power 3/2. So, correspondingly QM is already given as 0.5. So, QP we get as 0.5 into 10 to the power 3/2. So, that is about 15.81 cubic meter per second per meter. So, that is the second part of the question, and third part is we have to find out the pressure ratio. So, pressure ratio is Pm by Pp. So, that we can write as Lr rho r. So, we assume the density as constant. So, if you assume water is used in both cases, so we can assume density as constant. So, rho m is equal to rho p. So, rho r is equal to 1. So, correspondingly we can the pressure ratio will be Pr is equal to Lr. So, Pp the corresponding the prototype Pm will be divided by Lr. So, here Pm is given as 10. So, 10 into Lr is 1/10. So, 10 into 10. So, 100 centimeter of mercury. So, this is the third part of the problem, and fourth case is we have to determine the power ratio. So, power ratio is equal to energy loss per second. So, we can write as Pr is equal to rho r Lr to the power 7/2. So, rho r density is same. So, equal to 1. So, we can write the pressure ratio Pr is equal to Lr to the power 7/2. So, Pm is equal to Pp into Lr to the power 7/2. So, we can see here the model, the power used will be say 5000 is given here, the problem 5 kilowatt is given in the prototype. So, correspondingly 5000 into 1/10 to the power 7/2. So, that will be about 1.58 watt. So, this shows how we are utilizing the fruit model law corresponding to so to solve these kinds of problems. So, here we have considered the flow over a spillway. So, this problem is governed by the fruit number similarity, and then we have derived various parameters, and we get with respect to corresponding either with respect to prototype or the model, we can find out the various parameters. So, this is about the model similarity laws. And before closing this chapter now, we will discuss various model study aspect. So, say all this dimensional analysis or the dimensionless numbers or the similitude or the similarity principles which we consider, we use for the purpose of model study. So, as mentioned in the beginning, so this model study is very important, or modeling is an important tool in engineering studies. So, here you can see the model of a sump pump which we did in our hydraulics laboratory. So, here a channel, open channel, we have done a model corresponding to an open channel, and here we provide pump sump. So you can see this case was done for an industry. So, to see that what happens in the pump sump when a large quantity of water is pumped out. So, how the behavior, it is very difficult to use mathematical model, or theoretically it is very difficult to solve. So, we construct a model for this kinds of problem. So, this particular model we have constructed with respect to 1:8 scale with respect to the prototype, and then what we are studying is say what happens if this same amount of water is pumped using various pumps, how the disturbance, whether a lot of turbulence are generated or vorticity are generated. So, this is what we study here. So, this modeling is an important tool, and it represents the actual object in a smaller form or sometimes greater scale. So, depends upon the case, it can be a smaller scale or it can be a larger scale depending upon. So, we generally, as we have seen, we scale it to satisfy the various conditions, various similarity principles like geometric, kinematic and dynamic similitude. So, while do this kinds of, say for example, this particular model we have used the say fruit number law, and use all the corresponding similarity of geometric, kinematic, and so like that we can do either we can choose kinematic or geometric and kinematic, or say dynamic together depending upon various combinations of depending upon what kind of problem you are trying to model. We can have different kinds of combination. So, now say we have already seen say what are the purposes of hydraulic model study. So, as I mentioned, many cases are so complex, it is very difficult to represent theoretically or to do mathematical modeling. So, these model studies, hydraulic model studies are used to understand the phenomenon with respect to a realistic approach. So, you can see that we are using almost scale ratio, and we are trying to replicate the real case of the prototype in the laboratory. So, we can this is somewhat a realistic approach. So, we can understand the various phenomena, and then the second one is here you can see the problem complexity. So, here as I mentioned, say this particular sump pump model study which we did in our laboratory, hydraulic laboratory. So, it is very difficult to mathematically represent this turbulence or the vorticity formation with respect to this pumping, heavy amount of pumping. So, the mathematical model is difficult, and but the modeling, if you do appropriately with respect to scale, we can observe, we can see whether how the turbulence are generated, how much turbulence is generated, whether the pumps are affected or the system is stable. So, some case wherever theory cannot be directly solve the problem or mathematical modeling is difficult. So, then this physical modeling or hydraulic model study helps. So, models of dams, spillway, etc. Generally, so since a large investment is done for this while we construct a dam, so say other than the theoretical study or mathematical study, we generally do a model study, hydraulic model study. So, if you go to Central Water Processing Station in Pune, you can see number of model studies for various dams, spillways, etc. So, this modeling of dams, spillway, etc. So, first we test in the laboratory to get idea about various parameters and how the system will be behaving. So, then only we will be going for the real construction. So, this hydraulic model study is very important. So, while doing these kinds of model study, say we can see that so we have already seen the similarity principles like geometry, kinematic and dynamic similitude or similarity principles. So, as far as geometry is concerned, say different types of modeling is possible. So, first one is the undistorted model. So, the modeling can be either undistorted model or distorted model. So, undistorted models means the model is geometrically similar to the prototype. So, you can see the length wise, width wise, depth wise, all the geometry is concerned. The model replicate the prototype. So, the geometrical similarity is achieved and model results can be. So, since geometrically similar, many times most of the cases we can directly transfer the results with respect to the prototype. So, these kinds of models are called undistorted model. But sometimes, like if you do a modeling of a river, so in this particular case you can see, say if you are doing a modeling of a river like this, then you can see that the length parameters we can replicate, the width parameters we can replicate, but depth is considered, we cannot use the same scale. So, if you use the same scale, the depth may be say 2 meter, but width may be 200 meter and the length which may be considering maybe 2000 meter. So, you can see that if you use the same scale for the length, breadth and the depth, then you can see that the whatever we get to be very difficult to interpret and then modeling will be difficult. So, there we use cases for distorted model. So, here one or more terms of the model are not identical with the corresponding counterparts in the prototype. So, these kinds of models are called distorted models. So, actually whatever the results which we will be getting also distorted. So, we have to correspondingly do some rectifications, corrections after the results are obtained. So, but generally all these distorted models give qualitative values and then we can interpret accordingly. So, the models can be either distorted model or undistorted model. So, you can see the distortion of models. So, as I mentioned the river channel, so the depth is very difficult to represent. So, model with the geometry scales are different in each main direction. So, as a river model is usually designed for a larger horizontal scaling ratio than the vertical scale. So, distortion of say many times the practical case of modeling, we may have to go for the distorted model than undistorted, since undistorted model will be difficult to do in the laboratory with respect to the prototype. So, we may have to go for distorted model depending upon the case. So, here again say in the case of distorted model, so generally you can see that length and width are generally scaled to suit available space. So, say if you consider a river model or an estuary model, you can see that length and width we generally will be representing will be scaled to suit the available space, but vertical flow dimensions especially depth is considered. Say generally the gravitational effect is more important and fluid flow similarity is met. So, we will be making a distortion or we may not be able to meet the vertical flow scale. So, there a distorted scale is used. So, finally what happens is no geometrical similarity is achieved and then it becomes a distorted model. So, when this distorted models, when we use the distorted model, there will be definitely the scale effects. So, we have to consider the scale effects. So, many cases, so as I mentioned, we cannot do all the geometrical similarities. So, that is why we go for the distorted model. So, distorted model, so we have to, before going for a distorted model, we have to justify whether this kinds of modeling is say investing money and time and our efforts are say justifiable or not. So, say some of the cases here I have mentioned distorted models are justified. Say for example, if Reynolds number criteria can be neglected and pressure is nearly hydrostatic. So, say like what we have seen in the shallow water flow problems or estuary problems or some guys or river problems. So, here we assume that the pressure variation is nearly hydrostatic and the Reynolds number criteria can be neglected, and a distortion by effects other than the dominant one such as viscosity, surface tension we can neglect, and gravity is the dominant force. So, this is another case where we can justify distorted model. And then third case is amplification vertical scales. So, problem to simulate fluid resistance. So, most of the difficulties are that say in this kinds of river or the estuary models, what happens is these vertical scales are not met. So, the fluid resistance we have to say artificially simulate the roughness of the bottom or the boundaries may not be met. So, this we have to do some artificial reference or turbulence we may have to generate. So, amplification vertical scales is a major issue. So, while doing these kinds of models, we should be very careful the scale effects to be considered, and then corresponding say rectification to be say we have to do before the model results are transferred to the prototype for either for design or for construction purposes. So, now as I mentioned, the scale effect is a major problem. So, some of the examples on scale effect, say in a model the drag coefficient should be same as prototype if dynamic similarity is met, but you can see that the Reynolds number is smaller. So, in model, so theoretically drag coefficient should be greater as per the, so if you draw a graph of CD, the coefficient of drag versus the Reynolds number, then you can see that the Reynolds number is smaller in model. So, drag coefficient should be greater. So, also the drag force comprises of the foam drag and surface drag, but in many cases in small models surface drag might be predominant, the foam drag may not be predominant. So, we can see that there will be lot of scale effect. So, these are the problems while doing, say typically if you do the drag effects, if you consider for particular problems. So, these problems like the surface drag may be predominant and the foam drag may not be coming, and then the drag coefficient with respect to Reynolds number is smaller. In that case the coefficient of drag may not be truly representing whatever it should be. So, these are some of the scale effect which will be generally say we have to deal while doing the physical modeling, say for large structures or large say like rivers, estuaries, etc. So, before closing this chapter, so now let us see some of the important steps as far as the design of a physical model is concerned. So, some of the important steps are listed here. The first one is geometry scale ratio is to be selected within the constraints of the laboratory. So, this is important since say when we are modeling a river or a hydraulic structures like a dam or spillway. So, we have to see how much we can say the space available, and then how we can what can be the scale ratio. So, that is the first point, and second point is from the scale ratio and the similitude criterion, example food or Reynolds, discharge can be scaled properly in the model based upon the maximum discharge. So, the discharge in the prototype can be very high. So, correspondingly we have to scale down into the model. So, either we can use the Reynolds model law or the Fruits model law to do this discharge scaling. So, this is a second step. So, the discharge parameter, first step is the length parameter, second or the scale, the geometry is concerned, second one is the discharge parameter, and third one is check to be done if the Manning's roughness or friction factor can be achieved in the model. So, as we have seen the case of a river model or an estuary model, then it is very difficult to achieve the turbulence or the friction effect. So, say the third important step which we have to see is whether we can achieve the roughness coefficient like Manning's and or the friction factor, whether we can achieve in the modeling. So, this is the third step, and fourth step is Reynolds number or Foot number wherever applicable should be checked for minimum flow conditions. So, this is very important. So, when we do modeling, whether the minimum flow conditions with respect to the minimum flow conditions, whether the Reynolds number or Foot number whichever is applicable, we have to check whether it is achieved. So, this is the step number 4, and step number 5 is finally a convenient scale is chosen to satisfy all the similarity criterion whichever way possible, like geometry, kinematic or dynamic similarity. That is the fifth step. And sixth step is advanced modeling such as 2D model or distorted scale model like river model to be done in situation where simple physical models are not feasible. So, as I mentioned, like in the river or estuary problems, normal undistorted model will be difficult. So, we can consider a distorted scale model. And the seventh important point to be considered, for distorted model, horizontal vertical scales to chosen separately and appropriately. So, we have to consider the horizontal scales and the vertical scale appropriately, like as I mentioned, the river flow or the estuary flow. So, this say the depth wise is, or the vertical scale will be different and the horizontal scales will be different. So, now before closing this section, some of the models we say briefly discussing. So, first one is, as I mentioned earlier, one is the sump pump model. Modeling has been done in our hydraulics laboratory. So, this model has been built to one is state scale. So, here you can see the pumps are located here and a channel the forebay condition to simulate the forebay conditions. This is the flow coming, and then our aim here is to see the disturbance or the whether the forebay given is okay, or the turbulence generation, or what happens in this sump where the pumps are taking water. So, the disturbance. So, as I mentioned, theoretical development or application of theory or mathematical modeling is very difficult in this kinds of problem like sump pump. So, but if you do correspondingly a good model is developed, then you can see all the turbulence or all the say what is all the problems with respect to sump we can easily identify. So, this model has been built based upon the Froude number similarity, and then we have done a scaling of 1:8, and then we have found that say the existing design is okay. There is not much with respect to the pumping, not much disturbance are generated. So, that is what we proved through this sump pump model. Second case is model predicting the depth of cover around the bridge pier. So, here you can see a bridge, say bridge pier is here, and then this is the bridge and then a channel is there and the sandbed. So, this modeling is also done based upon the Froude number similarity, and then you can measure the various parameter with respect to the scour effect on the pier. So, this is a model with respect to bridge pier covering. And then as I mentioned, most of the time we will be doing the say before constructing a dam or spillway we will be doing physical modeling. So, that is very important, since that gives a lot of inputs before construction of the dam or spillway. So, here you can see here also we use the Froude number similarity. So, here is the reservoir and then the dam is, and then with respect to spillway we can construct model according to the appropriate scale, and then this shows a dam model with the spillway. And the third case here you can see a physical model of a river. So, either a straight channel we can construct like this in the laboratory using the Froude number similarity, and this you can see this here we use a distorted model. So, since the depth will be different and then other parameters length and width will be different. So, this is a meandering channel or river. So, here you can see the physical model, distorted model with respect to a river. And then this shows the physical model of an energy dissipator. So, energy dissipation we use say on the downstream side of the dam. So, you can see how the energy dissipators are placed in the model, and then we do the simulation. And then next case is the physical model of a port. So, you can see that the various channels are replicated and breakwater is replicated here in the model, appropriate scaling, and then say we can see say with respect to a ship comes, or if a new construction is made, then what happens, and the waves also will be simulated here, and in case tidal effect are there, that also simulated in this kinds of model. And here this shows the model of a dam wall with auxiliary spillway. So, this also, as I mentioned, very commonly we will be doing while before constructing spillways, we will be doing the modeling for spillway. So, this shows how we do for a spillway. So, finally, to summarize this chapter, So, we have seen the dimensional analysis, what are the importance of dimensional analysis, and we have seen the methodologies like Rayleigh's method, Buckingham pi theorems, and then also we have seen the importance of similarity or similitude. So, as we have seen here, the dimensional analysis is an important tool in analysis of parameters of any equation, and dimensional analysis gives the using dimensional analysis we can choose the relevant data and data relationships and analysis, and then the model similarity or model similitude with respect to geometrically or kinematically or dynamically, it is very important. So, similitude is very helpful in the development of engineering models, as we have already seen in this chapter. And finally, the model scales, we have to choose the model scale appropriately, say the Reynolds model law or Fruit's model law or other kinds of model law we can utilize. And also models, sometimes the model can be undistorted, and sometimes depending upon the case model can be distorted model. So, where in the case of, especially in the case of distorted model, we have to consider the scale effects, and we have seen the theory and application of this. And finally, as a final, where the model studies helps in understanding a physical system, and then we can analyze the system in a very simple way. So, the prototype, the real case, say we are replicating the laboratory to scale, and then we are studying it, and then finally what results we are getting, through that we are transferring with respect to the prototype design or construction or the operation of the prototype. So, this is about the dimensional analysis and its theory. So, further in this course we will be discussing topics like Navier-Stokes equations and applications, and the say drag, lift or the boundary layer theories and the pipe flow.